Alright, final problem. It says find the slant asymptote, and I was asked about what an asymptote is, just to verify. Slant asymptote here. An asymptote is a boundary of a graph that, for the most part, isn't crossed. Vertical asymptotes are never crossed. Horizontal asymptotes can be crossed near zero, but they're not crossed as you get towards infinity. Same with slant asymptotes. They can be crossed towards near zero, but not as you go towards infinity. It'll be boundaries. So basically what we'll get is a dotted line like this on our graph, and maybe our graph does something like this. I don't know what the graph does here, but it can cross towards, so if our x and y axes are like here and here, pretend that's vertical. Alright. If our axes are like there and there, near zero maybe it crosses, but as you go towards infinity it's going to hug the line but not cross it. So that's what it is. And if there were a vertical asymptote in this picture, I don't know, say there's a vertical asymptote also, maybe it's here. You won't get both a slant and a horizontal asymptote.
Okay.
But it might be something like this. So kind of just, it's kind of like an electric fence. The vertical asymptote is the most powerful electric fence in the world. It can't be crossed. The horizontal and slant asymptotes are not very powerful near zero, but as you get towards infinity and negative infinity, they're more powerful. The graph won't cross it.
Okay.
All right. And let's see here. So this one asks us for the slant asymptote. Just to let you know, if they don't ask you for the slant asymptote, but that your job, part of the job of graphing is to find all the asymptotes. What else we know? There's a slant asymptote in this problem. Highest power on top, x cubed. Highest power on the bottom, x squared. Every problem we've seen so far, the highest power has been the first term. In the homework, they jumble them up sometimes. So like maybe it's 2x cubed plus 5x to the fourth, or something like that. So be careful. Watch. Don't just focus on that first term. Look at the whole top, find the highest power. Whole bottom, find the highest power. If the highest power on top is exactly 1 bigger than the highest power on the bottom, it's going to have a slant asymptote.
Okay.
To find that, you simply have to do long division of this divided by that, including zero terms. So I've got x squared plus x plus 3 being divided into 2x cubed plus 5x squared plus 0x plus 1. Okay. Obviously synthetic division is not available on this one because we're not dividing by x plus or minus something, so we have to do long division. That's the bad news. The good news is when the power here is 1 less than the power there, there's only 2 things we got to go through. All right? And what we're looking for is a linear equation, x plus something. So 2x cubed divided by x squared is going to be 2x. 2x times x squared is 2x cubed. 2x times x is 2x squared. 2x times 3 is 6x. There are 3 objects here, so we get 3 terms here. As always, we're going to subtract the product. The product is a trinomial, so all 3 signs have to change. The first objects, as always, cancel. 2x cubed minus 2x cubed cancels. The remaining stuff just comes down. We get 3x squared minus 6x plus 1. Alright, then if I divide again, 3x squared divided by x squared is going to be plus 3. Now, I could continue on. All that this is going to do at this point is give me a remainder. So let me just show you, I'm just going to say right now, I'm going to put a little star right next to this. I can stop right here. That's the answer is y equals 2x plus 3. But just to show you the remaining part of this, I get 3x squared plus 3x plus 9. We change all the signs. Minus, minus, minus. Cancel, cancel. Negative 9x minus 8. Plus negative 9x minus 8 over x squared plus x plus 3. Right? The slant asymptote is all about going towards infinity. And in the process, I say ignore the remainder. Here's why you ignore the remainder. As x gets towards infinity, I have negative 9x over x squared, which reduces to negative 9 over x. That goes to 0. So as x gets extremely large, either positive or negative, that goes to 0, so that's irrelevant. So in essence, once I got to this point here, let me just back up. These are erasing stuff. There we go. That's where it starts. Okay. Once I get this and I get this and I do this divided by that equals this, that's the answer. You don't have to go further than that. That's all the synthetic division is ever going to be for a slant asymptote. You get the first one, do as is like normal. the second, all you have to do is that divided by that equals that. What happens after that's going to be a remainder. It's irrelevant. So y equals 2x plus 3 is the slant asymptote. And just to give you a visuals on this one, let's go back here, y equals, clear that out. All right, if I type in this function, 2x cubed plus 5x squared plus 1 divided by x squared plus x plus 3, that's my graph that I'm trying to graph. And if I just do a regular zoom, standard zoom 6, we can see what the graph looks like. There's some weird stuff there. There it is, okay? Nothing too fancy. Okay, if I type in y equals 2x plus 3, that's not good. 2x plus 3. We'll see our graph happening here again. There's our original graph. It's kind of interesting around 0, then it gets pretty straight after that. And then we get y equals 2x plus 3, maybe, there it is. And you see the graph is kind of approaching that line. If I extend the window out some, let's go negative 20 to 20 in all directions. There's our original graph. There's that little jump around there. And there's my line, and again the graph is close to it. Notice near 0 it crosses the slant asymptote. Again, it's allowed to cross around 0. As you get towards infinity, the line and the graph should resemble each other. Because again, the only difference between the line and the graph is that remainder. As x gets bigger and bigger and bigger, that remainder is getting closer to 0. So that the line and the graph are almost the same graph at that point. So that's all it's doing for us. It's giving us a boundary for that graph.